All right, so this is Group Six presentation or presentation of Group Six. Uh, we are presenting on input output in computer architecture and organization. So in this video, we are going to uh, present or discuss about input output in computer architecture and organization. So let's get right into it. So first of all, we need to know what input output systems are. So input output systems are essential components of the computer architecture that facilitates or enables communication between the CPU and external devices. So what are these external devices? We have keyboard, mice, printers, and all that, right? The main, you know, purpose of these input and output systems is to facilitate data transfer or communication between our computer and external devices. So without input output systems, our computers will not be able to communicate with any external device that is not part of the computer. Now, here are key functions of the input output system. You have data transfer, device control, error handling, and buffering. Now, for data transfer, that's the moving of data between the CPU, memory, and external devices. That's for data transfer. Device control is the management of device operations. For example, sending data from the keyboard to the monitor when you are typing, or reading from a disk during data transfer. Also, we have error handling. Error handling refers to the detecting and correcting of transmission errors, and also buffering. Buffering simply means temporarily storing data to manage speed mismatch between the device and the CPU. Now let's go ahead and look at the types of input output systems. The types of input output devices. Yes, since you are talking about the system, you need to know what the corresponding devices are. So we have input devices, uh, output devices, and storage devices. Now, for the input devices, these are peripherals that allow users to provide data and control signals. So, for example, the keyboard, the mice, all input devices, right? And output devices also display the information from the computer to the user. For example, monitors, speakers, printers, all output devices. And we have storage devices as well. Storage devices, the devices that are used for storing data. So, our hard drives, our solid state drives, USB drives, all that. Those are the types of input output devices. Now let's go back and look at categories of input output devices. Now there are three categories of input output devices: the human readable devices, the machine readable devices, and the communication devices. The human readable devices are designed for user interaction. So, example, keyboard, mice, monitors, printers. Basically, all inputs and output devices are human readable devices. And the machine readable devices, they are used for automated data exchange, right, between the CPU and the memory. So we have hard disk and SSDs, sensors, actuators. Communication devices are also they enable data transfer between computers. So the network interface card, the PCIs and all that, the modems and all those devices. So these are the categories of input output devices. Now let's quickly look at modules and their roles. So the functions of input output modules. You've already mentioned some error detection, buffering, device control. We mentioned it in the previous slide, so we'll skip that. Um, let's move on to components of an input output model. Yes, the components of an input output model. So, what makes up an input output model? We have the data registers, the status registers, and the control register. So, the data register holds data being transferred the status register indicates the device state. So for example, if you connect a device to your computer, let's say a mouse, right? If you connect a mouse to your computer, you receive some kind of notification or prompt that the device has been connected. Should there be an error in your device or in connecting your device, you will also receive an error message. So the status register is responsible for that. Control registers um, stores command from the CPU. So that's all for the modules and their roles. Now let's move on to the bus and interface standards. The bus and interface standards. So common input output buses that we have, right? For input output systems, they depend on, or they have buses and interface standards that they use. So that's what we are looking at. So some of the common input output buses are the PCI, that's the peripheral component interconnect, which is used for internal expansion. So for example, the graphic cards, maybe our computer doesn't have sufficient, the sufficient graphic card that we want it to have. So in order for us to add a graphic card to the computer, it is through the PCI that we can do that. And also the USB. USB, we all know what the USB is used for. Uh, we can connect, our controllers and other devices. Most of our devices use the USB, for connecting to our computers and all that. And then we have the SATA, or the Serial Advanced Technology Attachment. Now this SATA is a computer bus interface that is used for connecting storage devices like hard drives and solid state drives to a computer's motherboard. So that is the SATA. So examples where we can find SATA is our hard drives, our SSDs, because they are used for connecting it to the computer. And let's go to the interface standards. The interface standards. So these are the USB, the Thunderbolt, and then the HDMI, the high definition multimedia interface. Okay, now let's move on to the addressing techniques. The addressing techniques. So the CPU must locate and communicate with input output devices using addressing schemes. This is where the addressing techniques play a role in input output systems, right? So we have the memory mapped input output system, or the memory mapped IO. Now the IO devices are mapped into the system memory address space. We've already seen what IO devices are. So these IO devices, like keyboard, the keyboard is mapped into the system memory address space, right? So it's accessed using standard load store instructions. That's assembly language. It's accessed using standard load store instructions. The advantage here is that it simplifies programming, so no special input output instructions are needed. And we have the isolated input output. That's the ports, or the port mapped um, input output, or IO. This uses a separate input output address space, unlike the memory map, which is the system memory address space. This uses a separate memory address, a separate IO address space. It requires special in-out instructions, whereby the memory mapped, requires assembly language instructions. This just requires special in-out instructions. So the advantage here is that it prevents memory address space depletion. Now let's quickly look at techniques and input output techniques and methods. The input output techniques and methods, or the input output data techniques and methods. So we have the polling technique, or the polling method. And in the polling method, it's a method or a CPU technique that repeatedly checks an input output device's status, or it checks an input output device status. The pro here is that it is simple, but the con here, or the cons here, is that it's inefficient, for high-speed devices. Now moving on to the interrupts. The interrupts are signals to the CPU, they indicating processing needs. They are signals to the CPU indicating processing needs. This method is also very efficient, um, allowing asynchronous processing. We'll get to asynchronous processing shortly. Um, and we have the direct memory access. The DME. The direct memory access enables data transfer without CPU intervention. So the advantage here is that it drastically speeds up processes, especially for large data volumes. So the direct memory access looks like the best technique. Now let's move on to the processes and channels. Okay, sorry. Let's move on to processes and channels. So for large systems, they are dedicated, input output processors to handle the operations independently, right? So we have the processors, input output processors, and then the input output channels. So let's differentiate between these two. So the input output processors are specialized CPUs that execute input output programs. Yeah, just as how every processor executes programs, right? But this is for the input output. So they execute input output programs. Examples are the Intel 8089 input output coprocessor, and then we have the input output channels, and these are advanced input output controllers that execute channel programs. They execute channel programs, so they are used in high performance computing. So it looks like the input output channels are faster than the input output processes. Now, synchronous versus asynchronous input output. Synchronous versus asynchronous input output. Now let's look at what asynchronous input output is. So for asynchronous input output, the CPU and device operate in lockstep. What you are trying to say here is that the two processes, or sorry, the CPU and the device are initialized to the same state during system startup. They receive the same inputs. So during normal operation, the state of the two processes is identical from clock to clock. So that's what you are trying to say. When we say the CPU and device operate in lockstep, basically what you are saying is that the two processes are initialized to the same state during system startup. So the CPU and device, right? They uh, during startup they receive the same inputs. They basically receive the same inputs. So the states of the two processes are the same or identical. Example is programmed the polling, the polling technique we discussed earlier. And asynchronous input output. For asynchronous input output, the device operates independently. And then the CPU continues other tasks. So the difference here is that for the synchronous CPU and device, they operate together, right? They operate together, or they operate in lockstep, right? So whatever inputs are going to the CPU, that's the same input going to the device. But for the asynchronous, the device operates independently, and then the CPU continues other tasks. Examples of asynchronous input output is the interrupt driven input output, or the direct memory access. Now let's move on to performance metrics, input output performance metrics. We have data transfer rate, we have the latency, and we have throughput. So the performance of an input output system is based on these three metrics: data transfer rate, latency, throughput. What is data transfer rate? It measures the speed of data movement between inputs, output device, and system memory. That's what the data transfer rate does. Latency refers to the delay in starting data transfer after initiating an input-output operation, and throughput measures successful data transfers from input-out device to system over a set time. Throughput measures successful data transfers from input-out device to system over a set time. So these are the metrics or the performance metrics that input output system depend on. Data transfer rates basically measures the speed of the data transfer. Latency measures the delay in starting the operation, and throughput measures the successful data transfers. Okay, now moving on to the software and device drivers. Input output software and device drivers. Now, for every system, there are device drivers embedded in the system that is supposed to communicate with input output, devices. So these device drivers are essential for operating system hardware communication. And we have operating system support as well, which provides standard drivers and application uh, program interface, program programming interface or application programming interface for device integration. And we have the input output scheduling algorithms. So these are the software and the input output software and drivers. Let's move on to the future trends in input output technology. Future trends in input output technology. So we have things like the emerging input output interfaces, right? The interfaces we've discussed about the interfaces, right? SATA and the rest, right? Now, new interfaces such as the NVMe, meaning the non-volatile memory express, and Thunderbolt are designed to improve data transfer rates and reduce latency in modern systems. So, um, now we have new interfaces such as the NVMe's replacing the SATA. The SATA was the interface that our hard disks and SSDs were operating on, right? But the non-volatile memory express has come to overthrow that SATA because it is faster. So now most of the new SSDs coming out, they are all using the NVMe because it's very fast. It's faster than the SATA. It's very fast and it's very fast. Better than the SATA. And Thunderbolt as well. Also, we have the integration of AI in the input output systems. As you all know, AI is gradually taking over the world, so there's no surprise that it's also or it has also been integrated into our input output systems. And we also have the evolution of input output devices, right? So, a typical example is our hard disk drives, how we transition from the hard disk drive to the solid state drive. That's an evolution of input output device because the hard disk drive was slower and was also heavier. Yes, but the solid state drives are very fast and are lighter. So that's an evolution of the input output devices. So that's all for our presentation. Thank you all for your time.